Good morning, everyone. It's in the back. Did you find it? All right. Anybody else need a note sheet? We need a note sheet today. Did you grab one? We all have one? All right. So just want to look at the rest of the chapter. It's very short compared to most of them that we've done. So today we're going to talk about periodic trends. Most of you are, I think, you handed in your secret agent already. Make sure that you've done that, or else you can hand that in today. If you were not here yesterday, you will need to perform that activity and create a little table of secret agents and answer a few of those questions and draw a very complicated and very complex drawing of a unseen agent. Tomorrow we're going to do another project that's similar to the secret agents. It's a short period, being on a Thursday, so we'll kind of understand what Mendeleev was doing with discovering the periodic table, and you're going to kind of do the same things, and we'll discuss that in a moment, and you can hand that in at the end of the period as well. And then we'll review the materials that we've been talking about, and we will already have a test. It's more of a quest or a quiz on Monday. It won't be as big as a test, but it will be larger than a quiz. So if you want to do a twiz or a quest, it's your call on what you want to take, but they'll be the same thing. And that is when your poster is due. If you have that done early, you can hand that in early. If you are afraid that it could get ruined by putting it in the slot, very understandable, other people are putting things in there and it could get damaged, then I would drop that off on the front table of Mr. Blyford, Mr. Neubauer, or myself, and just make sure it's not somewhere random, making sure it's real obvious if we're not in that room at the time. Your name's on the back, all that good stuff, okay? So that kind of brings us to the end of this chapter already. It's very short. Make sure that you are looking at that review sheet that we created with all the names of the groups and things like that. So speaking of that, just want to, you don't have to write any of this down right now. Mendeleev, we talked about, was the founder of the periodic table. He went up basically to his cabin and he started putting out all these cards, and we're going to watch something right now, and started realizing properties matched up in a certain way. And, well, I will let this do the talking instead. This is on, nope, that's not it. We're not going to listen to that again. Wait, what? You want to? What? Of course.
The complexity of super dogs.
I miss old YouTube.
Hello, I'm Hank.
Can I watch about a 3-minute clip here? So just sit back.
Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know. Downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dmitry Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you know, you don't yet. But we're imagining. So it's the 1860s, and about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On the side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity, so the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little fuzzier. But not you. You become obsessed. Obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize that you're simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements, and when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data, and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you've created. And you know what the really crazy thing is? You're right. That French guy's data was wrong. You, never having examined the element he discovered, knew more about it than he did. Because you are Mendeleev, master of the elements. Okay, we're done imagining for the episode. That was fun, though. The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left.
All right. So, take it for what it's worth, but pretty cool fact that he basically discovered elements before they were discovered. And that is now the periodic table that we have today, and there are more elements, and it is more refined than it was. There are some issues with it. For example, the periodic table really almost should be wrapped around itself. That's pretty hard to put on posters and in textbooks and things like that. So we do have to kind of limit ourselves based on the display that we can have. So today, what we are going to do first, we're going to do a little review, and try not to look. Just going to do this in your head. If this ever works. There we go. So we learned a couple days ago about regions. There are 4 of them. Right? What's the largest region on the table? Region. They are simply the metals. Is that ever going to pop up? There we go. Those are the metals. We need to have that understanding. We need to be able to recognize that, okay? Second largest group. It's right here. The non-metals. I'm not sure how many clicks I need to do. And it's not that big. It's like, whoa, that's the second largest? Yep, that's the second largest because most of the table are metals. We are going to be learning more and more that if you're close to another element on the table, that means you have similar properties. So if you're in between here, you're kind of like a metal, you're kind of not like a metal. So we learned that these were called the semi-metals or the metalloids. So they kind of share similar properties of both. And then finally, the last region we have learned are the noble gases. So those are regions, okay? We also learned blocks. We learned this last chapter as well. And again, you're going to have to be able to recognize these. So it's based on electrons and how many electrons can fit in certain orbitals and sublevels. So we called this one the, what is that? That's the S, right? That's the P. The big one is the D. And those are the F's. Right. So can you recognize that? Like if I make put a table up like on the worksheet that you handed in yesterday, or the other day, periodic table 1, you just recognize it. Like if those are labeled and this is like an A, B, C, and a D, do you know that that's the S block and the D block and the P block and the F block? Lastly, and you do need to know these names. Can you recognize and know where they are? So the first group, anybody know? Anybody know what that's called? Alkali metals. We're going to go through all these, and then we're going to get in the topic of the day. Next one. Alkaline with an N-E-I-N-E, alkaline. It's not alkali earth metals, it's alkaline earth metals. Then it gets kind of nice. For the next four, it's based on those. There's no reason we should get these wrong. That is the boron group. It has boron on the top. Carbon group, nitrogen group, oxygen group. My favorite though then, people write this as the fluorine group, which I get it, I do. But those are the halogens, and then again, those are my noble gases, right? A couple other little spots. This whole thing, they all have a lot of names. Like this one is actually my favorite name of any group. This is the mint group, because they use those to mint coins, copper, silver, gold. They make coins out of it. Again, not spearmint, like gum. That'd be horrible tasting gum and somewhat poisonous. But as a whole, those are just my transition metals. Lastly, these are probably the two hardest to remember in my opinion, but how to kind of remember them, you will have access to a periodic table, is that it stems off of, and you can see these two are right here. This is lanthanum and actinum. So if you can even like, oh yeah, I remember that they're linked to those elements. Well, then we can have a chance, and those become lanthanids and actinids from lanthanum and actinum, which again, you'll have a periodic table which have those names. So those are all the groups in the families. And those are all great. And we need to be able to identify them. But there's a lot more going on in the table than just naming things. So today, forgot, hydrogen group. That one's tricky. So we have this on our coloring sheet. That's something that we need to be kind of thinking about. Like, I need to make sure that I have these names down. Don't study it the night before. Like, every once in a while, these are going to be the ones that are going to get you. Do I know these? It's under your control. It really is. That we're going to just be asking names for part of the test. All right, so on your sheet, right in the middle, here we go, we're engaged. There are a bunch of circles, okay? And what we're going to do, by being able to talk about all the things on the front of your sheet, and this is very user-friendly because you have a lot of things already written, you just need to write a couple descriptions on each one. We need to talk about the table. And we're talking about trends today. So a trend is not something that happens exactly all the time, like, hey, it always increases, or this thing always goes down. A trend is an overall feeling. Okay, it's an overall increase or decrease of something. That's what a trend is. Oh, they're having a trend. Like the stock market, it's trending up. That doesn't mean like tomorrow if it goes down once, like, oh my gosh, it's crashing. Like, no, it's trending up still. Like you're going to have moments of highs and lows, but what's the overall trend? It's the same kind of idea. When we look at the periodic table, it actually doesn't always increase in mass. Sometimes it actually goes down in mass, and then it goes back up. For example, iodine is actually 126.9, and the previous element is 127. It actually went down, but the overall trend is that the mass goes up. Okay, so this is what we're going to do. In the corner, please don't make it really large, we're going to take a very small section of the periodic table. So we're going to take the upper left portion of the S block, and we're going to just look at 4 elements. And by looking at 4, we can talk about the entire table. So that's kind of nice. Instead of talking about like 114 elements or so, we're going to talk about 4 of them. Okay, so if I look at lithium, beryllium, sodium, and magnesium, so I'm like cutting this out of my periodic table, we have some information we can learn. For example, this is element number 3. So it has 3 protons, and we learned that protons are in the nucleus. So it has a positive charge. It's really important. It's a positive charge in the middle of 3. This would have a positive 4. Below it would have 11, and then magnesium would have 12. And that's like the charge in my nucleus, which we're going to label in a moment nuclear charge. But we'll do that in a second. The other thing we learned already is about electrons. So hopefully this isn't a huge mystery that these two have 2 circles because they're on the 2nd energy level. So I have 2 energy levels. These have 3 circles because it's on the 3rd energy level. So we're going to place electrons, and we're going to do it in a much more simplistic way. If I were to ask the electron configuration of lithium, what would it be? It would be 1s2, 1s2, 2s1. So 1s2, 2s1, right? 2 in the first, 1 in the second, right? So it'd be 2 on the first level, 1 on the second, right? This is the 1s2, this is the 2s1. I'm just placing electrons, like just really generically. So what would be the difference with beryllium? Where would the other electron be? Because we're gaining one. On the first or the second level? On the second, right? So it would look like this. Right, that'd be 1s2, 2s2. Okay? So just make it nice and kind of, just so you can see it. This is going to be a very nice visual without having to do a lot of extra notes and work. By just doing this once, it'll actually apply to everything that's on this sheet. So this is our setup. Everything else will kind of go quicker once we have that down. You missed it. We're already on beryllium. Let's go. Down here, you have 1s2. Right? So you're always going to have 1s2. And now we're on the third row. So you could pile through all that. We got to go through the hydrogen helium and then through the whole second row and then end at the third. So the second one would have 2s2. What else would it be there? If you're looking at the whole thing, I'm trying to get to here. So 2s2, do all that. 2p6, so I need to add another 6. So that would be a total of 2 plus 6. I'd have 8. I'd have 8 total. So 8 in the middle row. And then the last one is 3s1. So it would have 1 dot. Okay, I'm just trying to show a visualization that's going to help us kind of relate some of these trends. So those are our 11 dots. So 1s2, 2s2, 2p6, and then 3s1. Okay? So then again, what's the difference from this one to this one? We're going to add one more electron in the outer one, right? So everything else is the same, right? 1s2, 2s2, 2p6, and then 3s2. All right. The whole point of this is to see this visually of where the electrons are by the nucleus and away from the nucleus, like as they are further and further away. So here's the thing. What is the difference? As we go down, what are we gaining? What's the big obvious thing that's gained? Levels. I'm gaining energy levels, right? So just make an arrow, make it pretty tight to the side, please, because we need to write on things. We are gaining energy levels going down, right? I have 2, now I have 3, I have 4. I'm gaining levels. Now, going to the right, and I'm not asking, the answer is not electrons. So what is something else we're gaining if it's not electrons going to the right? So going from here to here or here to here. What's the other thing you notice if it's not electrons? I thought I heard it. Protons. We are going to call that nuclear charge. It's a very fancy way of saying adding protons. What are we doing today? Well, we're just talking about, gaining and losing nuclear charge. Oh, here's some money. Thank you. It works. Just, you got to try it, but you got to be real confident when you do it. Because you sounded really, really brilliant. Well, it has to deal with the electrons being in the s orbital versus the s and the p orbital, and you're like, whoa, here's a 20. Don't worry about it. I don't need change. Thank you. All right, so here we go. Here's my picture that we just drew, and I'm going to talk about atomic radius. So, atomic radius. I hope we all agree, and this is not a math class. I'm going to try to not mess this up. I envision this accidentally dropping and rolling all the way across and being like, oh no. My daughter does that a lot with the toilet paper roll. I'll come into our bathroom, and it is completely all down. So then you try to roll it back up, and it's just like this fat now. It's like, thanks for doing that. The radius. If you're talking about a radius, I hope we all agree it's from the center to the outside, right? That's the radius. All the way across is a diameter, right? In this, it's really easy to do because it's like, well, this isn't as hard as I'd like it to be, but it's very, like, this is the outside. I can see it. Like, this is it. So from the center to the outside, very obvious. Here's the issue. Atoms are not definite. They have electron clouds. Like, literally the term cloudy, like, hey, do you remember the whereabouts? We were whereabouts on the eve of October 17th, 2013. I'm a little cloudy on those details. Like, you're not certain, okay? And you're not like, I'm a little cloudy on that. Sweet, you know exactly where you were. You are not sure. So what we have to do, and you can write this right underneath your periodic table or above it on atomic radius. Instead, we have to measure from the only spot that is solid, the only spot that actually is something that we are definitely able to measure with all certainty, and that's the nucleus. Whoops, wrong button. The nucleus. So nuclei is plural. I'd actually underline nuclei. You take half the distance, and then you can draw this little picture between the nuclei of two like atoms. So if you did that, and cut it in half, that would be the radius. And you will need to know this. So there's a couple pictures that we will have. I hope that kind of makes sense. Why do I write two like atoms? Because if you had a monster truck tire and a tricycle tire and you put them next to each other and took the diameter or the distance between the center of the two and cut it in half, it clearly isn't the radius of either one. Right? You got to have the same. You got to have two gold atoms or two silver atoms or two hydrogen atoms. And you can just make two circles. Heck, you can just put a line with another perpendicular line through it. Or this is just saying the diameter and it's being cut in half. So it's half the distance. All right, so here we go. This is what it's all about. This first one will help talk about all these other ones. It's about the size of the atom, okay? It's everything. It's about the size. So let's talk about this. What I'd like you to do is draw, instead of talking about what happens going down and what happens going across, that gets tricky then when I say, well, what happens if I go the other way? So draw an arrow literally on your periodic table just like I have. So you're doing it underneath atomic radius, right? You have 5 little periodic tables. So draw an arrow at an angle, just like I have. And make it nice and bold and obvious. Like the tables aren't there for us to be able to use as resources. It's more of just the visualization. As I move down the table, what do you think's happening to the size? Just look at them. It looks like they're increasing. I'm just going to show it. But I'm going to talk about why. And this is actually what the tricky part is. The moving down part is the easy one because it's very visual for you. Like you can see this go, whoa, yeah, I went from 2 levels to 3 levels to 4 levels to 5. Yeah, anywhere if I'm moving downward, the atom's going to get larger. Here's the thing that doesn't make sense. As I'm moving across, then why do I have D for decreasing? So it's increasing and decreasing. The reason why is what we wrote up there, nuclear charge, okay? The protons are like 1,000 times heavier than an electron. So think of it this way, the protons are in this like bunker, and they are solid, and they got this rope. This is actually one of my dance moves, by the way. You rope or you fish, and then you bring the other person, and then they have to come towards you. It kills. It just kills. You're stuck to the electrons, and maybe electrons are on like rollerblades or ice skates. You're always going to be stronger. Sorry, now I'm confusing you. I'm an electron now. So I'm weaker than my strong protons. So as I gain nuclear charge, even though I'm gaining another electron, that nuclear charge is getting stronger, and I'm pulling in those electrons more and more and more because they are not able to pull as hard as I can pull. So they will decrease as I move across because the nuclear charge is sucking in those electrons tighter and tighter and tighter. Then why does it get bigger again? Because I gain another energy level. And then it gets smaller and smaller and smaller and smaller. Gain an energy level, smaller and smaller and smaller, getting sucked in. Gain an energy level, and then it gets sucked in again. Balloons out, gets sucked in, balloons out, gets sucked in again because you're adding those protons. Okay? So if any atom, like if I ask you the difference between NB and CR, which one's bigger? Well, NB is closer to this corner. So NB would be larger. KR or B? Well, that's tricky because it seems like it's the same distance, right? Then you got to go based off of energy levels. This one's probably larger, and we're going to talk about that in a minute because there's more levels, even though it looks like they're about the same distance from it. And we'll get into all that. But closer you are to here, the bigger you are. The closer you are up to here, the smaller you are. Okay? So the largest atom on the table is francium. The smallest one is helium. All right. Let's move on to shielding effect. So, again, there's my picture. A shield. If I have a shield, what does it do? It protects, or what's something else? Something's coming at me, a bunch of arrows, it blocks, right? It blocks things. So there's a blocking effect that's going on. So this is the longest definition by far. Nothing else is that long. So you can draw your, oops, I'll get to the arrow in a second. What it is, and I wish I could draw this. I can't draw on here. You're blocking the nucleus to the outer electron, okay? So actually I would, I didn't want to underline too many things. There's three things going on here. There's the nucleus, there's the outer electrons, and there's the inner electrons. The shielding effect kind of helps with a lot of other trends. It's the reduction between the nucleus and the outer electrons due to the shielding of the inner electrons. And once we kind of talk about it, hopefully it'll make some sense. It affects the size of the atom. Bless you. So we have two arrows this time instead of one. So we're going to draw an arrow down and then one that's over. Okay. So I'm using these every time. If I'm moving down, what is happening? The nucleus is trying to bring, like the cloud, the size of the atom is only as big, is as large as where the last electron is. So if that last electron is really far away, my atom's really big. If I can get it really close, the atom's really small. So it's based on where that electron is. It's based on where this electron is. So this nucleus is pulling in that electron. So there's an attraction force. The problem is, think of it like space. You got this asteroid field. These two electrons are getting in the way. Okay? I mean, you can think of it like I'm holding something and something else is hitting my arm. It's like messing up my attraction force. So if I move down one, check this out. The nucleus from here to here, look at all that stuff that's in the way. There's more. So what happens is this force gets weakened because of these inner electrons. And the shielding effect increases, meaning that the size of the atom actually gets even larger as you move down because you're adding more and more, basically, disturbance of inner electrons. I'm gaining inner electrons. Like I only have 2 here, now I have 10. So it's getting in the way. And you could be like, well, yeah, but there's 11 protons now. Right, but it's further away. There's more debris. There's more electrons between the nucleus and the outer electrons. But when I move across, check this out. Where do I add the electrons? On the outer electrons. So I have 2 inner electrons. I have 2 inner electrons. I have 10 inner electrons. I still have 10. I'm adding only on the outside. So what's happening to my shielding? Nothing. There's no more that's being added that's messing up that pull. There's nothing more. Like it doesn't make it, which that makes sense that's why it gets smaller. If I was adding more on the inside, the electrons could get away from my pull. It's all about the pull today. It's like, okay, my nucleus is holding on to that outer electron. Try to hold on to something today on each of these that you can go back to. It's the size of the atom because my nucleus is trying to hold on to the outer electron. Okay? And how well it holds on to it means that it's smaller or it's larger. The further it is away, the bigger it's going to be. And in this case, there's nothing else getting in the way. There's still 2, there's still 2, there's still 10, there's 10 here, there's still only 10 here. So the shielding doesn't make it worse. And it's just it's a byproduct of the energy levels in the electrons. So that shielding effect, those are our arrows. Those are unique. Everything else would be very similar, okay? So we have 3 more. Ionization energy. Told you that was the longest thing by far. Ionization energy. Ion is an atom with a charge. So ionization energy is the energy required to remove an electron, okay? So, told you it's all about the size of the atom. Where are the largest atoms? Lower left or upper right? Largest. Lower left, okay? I know he's not doing well lately, but Eddie Lacy, when he's running, he doesn't get the ball and start running into the line like this, okay? He tucks it in, right? He tucks it in. So, any object, if you want to get this away from me, it's hopefully pretty logical. Is it easier to take it from me here or take it in from me here? And some of you are like, I'm taking it regardless. Good luck. No. This is much easier to take away from someone than when it's close and being held tighter, okay? It's the same idea with the atoms. So the lower left are the largest atoms. That means my electron is really far away. Can you take it? Go. Oh, I let him do it. But he can take it. Now, if I hold it really tight, I'm not even going to let you try it. It's going to be much more difficult. So the big atoms, would it take more or less energy here versus here? More or less energy. It would take a lot less effort, right? So it's about the energy